So good afternoon. Today I would like to talk a little bit more about the research we did on competence-based training and virtual reality to actually show how we can more efficiently train without burdening the experienced workers, which are mainly scarce at the moment as we see in industry. And I will first show you a small outline on what I want to talk about. So first I want to show you where do we see the potential at the moment in VR training in the industry. Where do we think we need personalization in this? Because we know there's already a lot of VR training, but what kind of extra dimensions do we see there? And we use that, or we approach that in the concept of adaptive learning. And that adaptive learning, I will also show how we apply that to VR and also to realistic industrial use cases. On the other hand, we can come up with concepts, of course, but we also want to see what the impact is of going for such approaches instead of going for the more standardized tools in VR that we know so far. And then I also want to show how we can go from research, what we are doing, to integrating this more efficiently in the industry. Then I will conclude at the end, and as was mentioned before, later on we can have some discussions if you want in the bar. So the potential we currently see for VR training in industry, we all know that it's very difficult at the moment to find suitable or appropriate workers and to keep them for long term within the company. On the other hand, we also see that it's a very scarce thing, having experienced workers at the moment. So we also don't want to waste their time, to call it like that, in using their time to educate other people in the company. So we want to keep them as efficient, integrated in the production line. Also often, as you can see here at the fair as well, we have very expensive machinery. So if we have to allocate that machinery all the time for training, it would have a big impact on our production. So if we can reduce that as much as possible with VR, of course we can see that as a clear advantage at the moment. Also, we know that VR training actually gives us a very safe environment. And on the other hand, compared to, for example, on-the-job training in a company, we can automatically assess how well someone is performing. So we know right away what the learning progress is, how efficient this training was, where the positive points were in this training, where maybe someone has to train a little bit more. So it gives us a good idea right away, while in an on-job training, it's more a subjective feeling on how that training went. So looking at those different potential advantages, we took this further and checked what's already there in VR training and where can we take some further steps. And one of the steps we had in mind was how can we focus more on personalizations. In other learning systems, we also see that a one-size-fits-all solution is usually not the most effective to go for. Still, we see in VR training that often there's one solution for certain training, which is not really adaptable to the situation or to the person. Also within a company and in general, we see that operators differ on a lot of levels. They have different competencies, different skills. They vary in the levels in those competencies or skills. They have different cultural backgrounds. They speak different languages. They have other preferences in learning. So we see that we have sufficient reasons to go for the personalized method in VR training as well. If we look at existing learning methods in general, not only VR, we see that adaptive learning is a proven approach in this direction. I will talk a little bit more now on how we see that adaptive learning in VR. So if we first look at that method, it's actually a method of learning where we want to customize the learning strategy or the learning or the training to everyone individually as much as possible. That means that we get to an individual learning path, but also an individual learning pace. Everyone picks their own pace that seems to be the most efficient for that person. We see that that's mainly applied so far in learning management systems, but there's also an interesting theory that comes with that, which is called the cognitive learning load theory, which actually says that we shouldn't overload someone right away with a lot of information when we want to learn something. But on the other hand, we want to trigger them sufficiently to make the training efficient. So we have to find that balance in keeping them engaged, keeping them motivated, but not overloading them too fast with a lot of information. And that's what we want to apply in VR training. So if we focus or shift a bit to that VR context, we see actually that VR offers a few interesting features that we don't use optimally yet. We have hand tracking that's built in the headset, and many devices so far now also have eye tracking. For the hand tracking, we know at any point of time with which virtual object someone is interacting, for how long. On the other hand, with eye tracking, we know what's the user looking at. Is he searching for information? Is he looking at the right part of the VR training? So we actually know a lot with using those two features, which is not used that much so far as we see in VR training. So actually the goal is, by using that we can provide adaptive support and dynamic feedback in real time. That we can decide at the moment, we see that someone is struggling or more proficient with this or this, so we need more or less support at this moment in the training. So if you look a bit more in detail, how did we do that in an assembly kind of context, as an illustrative example? We have contextual data. In VR, we know at every moment in time, this is the task sequence of the training. This is a task where someone is at the moment training for. This is what we expect more or less as a duration for this task. One task can be a bit shorter, one task can be a bit longer. And we know what kind of feedback can we offer for this task to this person. On the other hand, we get some performance or user data, like how is the user performing at this moment? How much time is he spending in the current task? What kind of mistakes is he maybe making? And what can we do about, what can we do with those mistakes? How can we help that person at that moment? And then we come back with what I was just talking about. How can we use the hand tracking, so the detection of the objects in VR, and how can we use the eye tracking to know where is someone looking at and what can we do with that information. Maybe someone's looking all the time at the instructions, so we know the action is not yet clear in the training. Maybe he's looking around on the table, like what object should I pick at this moment? Or maybe he's already holding the right object and we know he's looking like what can I do with this object. So we have a lot of information from different perspectives that we want to use to personalize the training. We call this the sources of adaptation. It's actually the source, or like the source data that we can use to adapt our VR scene at the moment to that person automatically. So how do we use those sources? We actually call it failure states. We want to detect what kind of mistakes can a person make at this point in the training. And I will illustrate it later on with a specific example. But based on the mistakes someone is making, we can decide what kind of support does the person need. And the interesting thing here is you can actually approach it in a very flexible way. For each use case, you can define these can be the type of mistakes that can be made. And on the other hand, this is the kind of support that we want to give for this type of mistake. So if we look at an example, imagine we have, like I said, an assembly case where we have mainly pick and place operations. It can be that someone doesn't know what object he should pick in that step. So we can detect there's maybe an object failure. The person doesn't know what object to pick. What can we do? We can highlight that the one he's holding at the moment is not the correct one. We make it red, or we take a step further. We already make the correct one green to push him a bit more to know right away, this is the object you have to be working with in this step. Then you have other examples of failures. Maybe someone knows immediately, this is the bolt I should work with, but I don't remember where I have to assemble it. And then again, you can decide what kind of support do I want to give at this point for this person. And in the end, we want to look at each task individually, like what kind of mistakes can happen, what kind of support can we give. Maybe for a screwing operation, we want to show what specific screwdriver he has to pick. Maybe for something else, we want to take a different approach. On the other hand, we don't only want to look at a task level, we also want to check how is someone performing in the previous training sessions. If we know that all the tasks where a screwdriver was needed was always a bit of a struggle or a bit more difficult, we can support someone in the next iteration right away because we know it's usually a bit of a problem training this part of the full training. So we can take that fully into account and over time gradually decrease that support to trigger them, like in terms of the cognitive load theory I was talking about, to trigger them sufficiently to actually learn and by reducing actually that support that they get triggered sufficiently. So if I want to apply this in a realistic concept or context, We looked at a more easy assembly case where we had mainly pick and place operations. And there it's maybe sufficient to only use highlighting in the environment, highlighting when is someone holding the correct object, when is someone holding the wrong object, where should he assemble that object, and maybe along with that show some visual instructions. We also had a more complex assembly case. It was an electrical cabinet. And there you don't only have pick and place operations, but also a bit more complex wiring that should be applied and also screwing. So there maybe it's not sufficient to have the highlighting and the instructions, but we only maybe need animations to show, like, here you have to make this rotation with a screwdriver, here you have to do this movement to assemble the cables. And that's actually the flexibility I was talking about. For each use case, you can define what kind of support do I want to give in this situation. I actually want to compare it now a little bit with how we see traditional training to actually show where the adaptive approach differs from what we usually do. So with traditional training, we always have the same amount of feedback and instructions. You start a training, they help you along with it, and you see what's happening. You do the same as what's happening in the VR training. For every trainee, it will happen exactly the same way. Maybe the duration will vary a little bit, but in the end, everyone gets the same support, the same training. So if you looked in the video, you will see that, for example, you get highlighting right away. You see, I have to pick this object, I have to place it there, and it will happen through all the steps. And everyone will get the same support. Then if you would go to the adaptive training, you actually want to adapt that feedback. You don't want to overload an expert with all that information if he already knows what to do. Maybe he only needs a little bit more support on a certain task in that training. So there we can, at the spot, decide how will we support someone. So if we look at that video, you will see that at the start there's no highlighting or other kind of help except for a basic instruction. If we then see when a timer has passed, now an example for easiness is just put on 10 seconds, we can show, we see that you have trouble finding the right component, we will highlight it for you. But we will not highlight yet where you have to assemble it. We will give you some time to figure it out, to think about it, to trigger you. If we see that, again, after a certain time limit, you're not able to fulfill this task, we will help you again. And that's a bit the example of what I was giving before with the failure states and the support systems. And over time, through each training session, we can decide how we can gradually reduce that feedback, because we assume that they are learning, and we can decide in the tasks where they're already more proficient, we can leave out the support or the feedback to trigger them, and the tasks that are still a bit more difficult, we can leave the feedback as needed. So we can create a fully adaptive experience and personalize it for everyone based on their experience or their progress within the training. Of course, I can talk about this concept, but it's also important to validate this, to show like what can be the impact of such an adaptive approach. For that, we did an experiment with 36 participants, and we gave them the compressor case I was just talking about as an illustration or an illustrative example. And we gave them a training session of max 20 minutes. We told them, like, here in VR, you can train for 20 minutes, but you have to make sure you know this kind of use case. You have to assemble it physically later on. So we gave them 20 minutes, but we actually split the group in 3, and for each of them, we applied a different strategy. For the first group, we said, you get our adaptive approach. They don't know about the other ones that exist. With the second group, we gave the same adaptive approach, but we gave them the control on when to decide when they want that kind of help or not. So the algorithm was still deciding, in this situation, I would help you in this or this way, but the user or the trainee was deciding, now I want this help and now I don't want it. So to see how they would decide getting feedback or support. And the third one was the traditional variation, where they have feedback all the time present, as we see in traditional VR training. And of course, it's very important, especially with VR training. It has, of course, limitations with physical haptic feedback. So we want them to make the physical assembly afterwards. We kept the case simplistic enough that they were able, with 20 minutes of training, to assemble that case without extra paper instructions. So right after the training, we asked them assemble this case, and we asked them also to come back 1 week later, because it's also important to see on a longer term perspective how much of the training is still being remembered at that moment in time. So if we then look at the main findings of that study, after the training, like right after the training they received when performing that physical assembly, we saw that actually in the adaptive group there were 80% less severe errors. But with severe errors, I mean starting with the assembly and messing it up at some point in time, that they cannot go further, that they need help, or that they say my assembly is finished, but it doesn't match with what we expected. Less severe errors can be that you assemble something wrong, detect it yourself immediately, and solve it. So we only looked at the severe errors because they impact the final result. After training, like I mentioned, it was 80% less in the adaptive groups. After 1 week, it was still 22% of severe errors in the adaptive variance, like looking at the errors again. We also looked at other components that impact your learning experience. For example, the mental load. If a training is more mentally demanding, there's also a big chance that it's less motivating to do because it feels more demanding for you, and maybe you get less engaged after some time. If your mental load is lower, you can train for a longer time more efficiently. So also there in the adaptive variant, we saw that they reported 28% less mental load on a questionnaire we provided. The same in terms of perceived efforts. They had to fill out a standardized questionnaire on the effort they perceived in doing that training and performing that physical assembly. Also there we saw a 43% reduction in the adaptive variance. Perceived performance was also something we investigated because it can boost your confidence. If you feel more confident and successful in doing that training and assembly, you also feel that you're more proficient in doing this. And there we saw an increase of 31% in the adaptive variance. Again, a positive effect. Also regarding stress and frustration. Again, this is important if you want to keep people motivated to do your training and to increase their potential. It's important that they don't get too much stressed in that situation. And for adaptive variance, again, we saw a 60% reduction. And last, but I think not least, the feeling of time pressure, that you have to feel like, I have to rush to get this done, to get this physical assembly done. We saw there was a reduction of 37% in the adaptive variance, which means that even with the same amount of training time, they feel less rushed, they feel more confident in knowing this training, and they feel better or they perform better in actually then doing the physical assembly. But if we then look at the industrial integration or application, of course, the study I presented, it was a smaller concept. It was a 20-minute training, again, with 1 week later, a repetition of the physical assembly. But it's important, if we want to bring this to the industry, that we don't only look at the task level like we did now. Like, example, we have in an assembly training 15 tasks. We look at each task separately. But of course, if 3 of your tasks, let's say here task A, B, and E, all have a screwing operation, we actually maybe want to group it. But in our approach so far, we still looked at a separate level. Where the disadvantage can be that maybe in one screwing operation you give less support, in the next one you see, oh, there's more support needed, so you label what kind of screwdriver should be taken, and you also highlight maybe the correct screwdriver. But you don't really link the different tasks with each other, so you can have a few challenges. There's a limited knowledge transfer across those tasks. You see they're really split from each other. And maybe we need more repetition to really master the skill because we are all considering those tasks individually. What we actually want to do and what we are working on at the moment is bring this to a more competence level. So how did we implement this VR training at the moment is actually grouping tasks. If we see in those 15 tasks in this assembly case, that task A, B, and E, to take the same example again, all involve a screwing operation, then they probably need the same kind of support throughout these 3 tasks. And maybe also the other way around. If we know that they are very proficient at screwing, maybe we can leave out these 3 tasks in the training to make it even more efficient. So we group the evaluation and the support. But if we, for example, see in task A, we still give a lot of support, we do the same in task E, B, and E. But if we see that they get more proficient, we can still decide real time, now from next time on, we can reduce the feedback because everything went well. So the real-time support is still there, but we consider it more from a grouped competence level. What are some potential advantages here? We expect, because you can skip some tasks if you want, or because you group them, that the learning curve can become even more efficient, and that we maybe see more advantages than I only showed in the findings. Training probably also becomes more efficient. You learn to link different kind of screwing operations with each other. So you also learn that, if I get more proficient in task A and B, I know I can also do task E. And, which is also a very important factor in my opinion, is that we can more closely align with the current competence management systems in companies. So in many companies you see that they have competence management systems where they actually keep track of the competences of their operators. For each kind of skill, for example welding, drilling, screwing, they give them a score. In some cases we see that's, for example, a number from 1 to 4. And we could check how we can link that with our approach. So we don't only stick to the task level I was talking about, but we can really rely on the existing structure within a company. So if we look at some examples, if we would take that 1 to 4 scale, one can be a novice user or operator on a certain competence. But for maybe another competence, he can already be an expert. So if we take the example of the screwing, maybe he's very proficient in screwing, but less in welding. In the training, we can take that information to already decide what kind of support do I want to give this person in the training. And actually the goal is, in the end then, is to ensure that our training is not efficient in itself, but also efficient in terms of aligning with the current structure or competence management systems within the industry. That it's more easy to integrate these kind of solutions, because we see a lot of VR training solutions present, but it's still hard to take that step from a research or a development level to bring it really to the companies itself. So it's really important that we align on that level as well. Of course, in the beginning I mentioned a few advantages of VR training. We also know that there are a few limitations. You miss a bit the physical haptic feedback when you're interacting in VR. So therefore, we also want to look at how can we bring this adaptive learning concept to other technologies. If we look, for example, at augmented reality, we know that haptic feedback is a bit more present there. We can look at what kind of sources of adaptation can we use there. Do we know some other kind of behavior, not only interacting with virtual objects, but also maybe how long is someone performing a certain step, and see if we can apply in the end the same adaptive learning concept. On the other hand, we see in companies that they work often with digital work instructions. This can consist of a picture or a video. And actually with video we can apply a bit of the same concept, or we hope to apply the same concept. In a video you can, for example, detect when is someone pausing a video. Maybe we can assume then that someone is not that proficient yet with that step. Maybe someone is replaying or repeating a certain part of the video. Again, an indication that maybe more support is needed there. And that's where we want to see if we can apply the same concept using other sources of adaptations, and then maybe play the same video with more oral, an oral description describing the task, or maybe showing another video explaining more what should happen with the reasoning for that we can actually do the same kind of support automatically and dynamically as we were showing in the VR concept. So we are currently working on that. But to come back and to conclude, we actually showed adaptive learning concept in virtual reality, where we focus on flexible and personalized VR learning, where we want to provide some real-time support to that person to make it personalized, where we use hand and eye tracking, which is not used that much before within VR training. On the other hand, to come back shortly to the improvements we saw, comparing the adaptive training versus the traditional training, we saw that we can see improvement in the amount of errors that are made, the time pressure that was experienced during the training and the physical assembly, the perceived stress and frustration, the mental load that was experienced, the perceived performance, which has a big impact on confidence, and the perceived effort during those kind of trainings. So that was my presentation. I hope I could bring you some new potential ideas about VR training in industry, and I'm happy to discuss this further in the bar later on. Thank you.